Hi, my name is Edison Carrillo. I'm from Ecuador and I'm actually pursuing a master's degree in optoelectronics from the University of Buenos Aires in Argentina. In this work, we present an optical quasi-point ultrasound detector that is intended for optoacoustic tomography. This technique of ultrasound imaging requires the measurement of low amplitude and a large bandwidth pressure pulse from several positions in space without introducing significant levels of distortion. Therefore, the geometry of the sensing region, the sensitive, and the linearity of the sensor are of critical importance. Where we propose to analyze a simple optical system that is based in a glass prism that is placed in contact with water. This system takes advantage of light as a sensing mechanism. We find 6 different properties of the optical file that could be used from sensing the ultrasound that are either based on the intensity of the phase. It's known that the amplitude to low pressure ultrasound waves in water is proportional to change in the refractive index. In order to track ultrasound pressure pulse that originate in water bath, we will use an optical system operating at fixed angle and wavelength to monitor the index of refraction at a point in space. This will allow us to determine the ultrasound file at a point, like a picture. The characteristics of the reflect beam depend on the Fresnel coefficient associated with the interface. In a glass-water interface, there is always a critical angle. For angles of incidence lower than a critical angle, the coefficients are real and depend on both refractive index and the angle of incidence. As we approach the critical angle, the reflectivity rapidly rises to 1. On the other hand, for angles of incidence greater than the critical, the coefficient became complex, with modules 1, and their phase depend on the refractive index and the angle of incidence. This phenomenon is known as a total internal reflection. As we can see, a little displacement from the critical angle produces a great rise in the phase. Where we plot the dependence of the module and phase of the coefficients for 5 different commercial classes that cover a wide range of refractive index. Since ultrasound pressure pulses are translated into refractive index change, the detection system we propose senses small refractive index variation through intensity change in the reflected beam. For angles of incidence lower than critical, the system tracks change in the amplitude of the reflected beam. Therefore, a photo detection system directly senses its intensity variation. Here, we plot the reflectivity of the S component as a function of the refractive index of water. The correlation coefficient is close to unity and evaluates the first-order approximation. For angles of incidence greater than the critical, the system tracks change in the phase of the reflected beam. Therefore, in this case, an optical interferometer has been arranged in order to translate the phase changes into intensity variation of the optical beam. For the phase, we plot the phase of the S component as a function of the refractive index of water and find that the first-order approximation is also switchable. For both detection modes, amplitude and phase, a differential mode, S-P, from the example, can be implemented with the advantage of reducing the effects of the intensity fluctuation. As all functions are monotonous, we also obtain a linear behavior but with a smaller slope, where we find 6 different modes of operation. 3 of them are based on the amplitude of the reflected beam, and the other 3 depend on the phase. A key parameter to evaluate their performance is sensitivity. This is for reflectivity and this is for the phase. Sensitivity can be adjusted by means of the index of refraction of the prisms and the angle of incidence. Here we show the sensitivity as a function of the angle of incidence, for the amplitude, for the phase, and the differential detection modes. As expected, the behavior shows that as incidence is closer to the critical angle, the sensitivity increases. For detection modes based on a single component, S or P, similar trends are observed except for the P component. We obtain higher values of sensitivity. In both cases, the higher values of sensitivity are obtained with the prism with the lowest index of refraction. However, as index of refraction of the prism decreases, the critical angle increases, and for higher sensitivity, increasing incidence may be required. In the case of the differential modes, either amplitude or phase, the behavior of the sensitivity curve is similar, but they are reach lower sensitivities. Here, the higher sensitivity are obtained with higher refraction in the prism. Finally, as a general rule, the sensitivities obtained with the amplitude detection are higher than those obtained with the phase detection. It's interesting to have a quantitative measure of the behavior regarding linearity such as